Hey folks, this is Robert Quinn here, your LinkedIn semiconductor industry content provider. Today, I would like to welcome Dr. Naveed Sherwani to the show. Naveed is a world-renowned chip expert, researcher, author, serial entrepreneur, academician, and a philanthropist. Naveed has founded 18 companies, and he has raised over $1 billion of funding from marquee investors. Naveed is currently the CEO of RapidSilicon, a company that brings creativity to FPGA design by combining the open source FPGA methodology with technologies that enable a faster design to silicon turnaround. Naveed, welcome to the show, and thank you for coming to meet with me today.
Robert, glad to be here. Thank you so much.
Naveed, can you give me a 30,000-foot view from your viewpoint, overview of the Internet of Things industry? Because so many of my followers are from semiconductor manufacturing industry. Can you explain how this will drive the semiconductor industry in the future?
How will we drive the semiconductor industry in the future?
So I think how the Internet of Things will drive the
Internet of Things. So I think among all the countries that I visit, I spent some time in China, in some parts of Europe. I think some of those countries have taken Internet of Things a little bit more seriously in the sense they've deployed it. So now you can see the value of that happening. So if you go to some of the modern factories, you can see that it's been replaced by robots. Each robot has many, many sensors on them. They're collecting data from all those sensors. I went to a factory which makes microwave ovens. They showed me a normal factory, 1,200 people working, and then they showed me a next generation factory enabled by IoT, and they had 20 people working. From 1,200 to 20, and this factory is better in terms of reliability and quality and on-time performance. And the sensor data is being collected from all the robots, from all assembly lines. It's connected by some FPGAs are there, some AI is there. So the sensor data is filtered, curated right there at the sensor. Whatever needs to go to the data center goes to data center. And then they can analyze in real time what is happening on the factory floor. They can connect that to the supply chain coming in. They can connect to the supply chain going out. So they can connect this whole thing together, making the factory extremely, extremely efficient. Wow. Now, if you can do that across the entire supply chain, then you do it across the city, then you do it across the nation, and then you do it across the nations around the whole world, you can see a fully connected supply chain. This is just one example of Internet of Things can change. Same thing applies to hospitals. Same thing applies to schools and education. Same thing applies to how we live and entertain. So I think in a world where we can collect data in real time, curated data, which is intelligent data, act on it, I think it improves the world in every which way. It makes it more efficient. It makes it safer. It makes it pleasurable. It makes it more knowledgeable. So I think it has taken us a long time to make Internet of Things happen because it needed a few things. It needed AI, which we didn't have before, because otherwise you're just collecting a lot of raw data, which is not useful. Secondly, it also needed 5G, which we did not have before, because you need to be able to transmit the data. Then you need a whole host of sensors, which some we had, but many of them had very high power, which is not what we need. We need low power sensors. So I think it took us good 15 years to get here where we are now. But in the next 5, 10, 15 years, I see a revolution happening across the world, from our homes to where we live, in our cities, in our cars, in our factories. So I'm excited. I think it has taken a lot of work to get here. It is still going to take a lot of work to get where we need to go. But there are examples in the world today where you can see what Internet of Things fully integrated into the system can do magic, and you can go see that today.
That's incredible. That's incredible. That's and can you also paint a picture and explain what the AI edge is? And so much of this is integrated into what the AI edge is, what FPGA is, and what open source is. So and how that's so critical to the Internet of Things coming forward to us.
Yeah, so I think for us, to be able to operate in any real world scenario, just like a human does. Human collects a lot of data. So which means we have a lot of sensors. We have sensors which can detect light, smell, motion, distancing, and a lot of those sensors, and they're all integrated, which we call sensor fusion. They're integrated sensors. We can collect the data, and right there we can also decide what is not information, just not interesting. Like if you're walking on a street, you could totally ignore everything that is happening around you unless a car is coming over and is about to hit you. How your brain can immediately focus on that thing and not focus, and not even, you sometimes don't even remember when you walked on the street what was around you, because it's not important. So you can do that with all your senses, and you can combine the senses to make meaningful, real value information to yourself. So I think the AI on the edge is that intelligence, that a raw data is coming in. You're looking at a picture is not interesting unless something in the picture that you say, I'm looking for, let's say you're waiting for, it's a camera where it's a stop sign. So you might see 99% of the time, no car coming. So there is no need to transmit that picture. Finally, a car comes, even that is not interesting. A car that doesn't stop at the stop sign, that is interesting. So the sensor, if it is intelligent to know, the car did not stop. So I need to look at the number plate of that car, and every car that stopped legally, ignore that. Every car that didn't come and with empty sign, ignore that. So now you can see that you're interested in 0.0001% of the data. If you don't do that, you're sending the entire raw video or image up, which will overwhelm your broadcast system. It will overwhelm your data system, and you got all the useless information, and then you discard it. So intelligence on the edge means analyze the data, and just like I gave the example of a smart stop sign, I think in US, we can use stop sign. And I can tell you one thing, that some studies have been done. Even if people put a sign on the stop sign saying it's a smart stop sign, even if it has no smarts in it, it will increase the compliance.
Sure.
Okay, you know what I'm saying? If people feel that this stop sign will take my picture, if I don't stop, it will immediately transmit my picture to the Department of Motor Vehicles and I will get a ticket. Let's say they did that, and did that with only few of the stop signs, and the rest of the stop signs just said it is a smart sign. They don't know which is a smart stop sign, and we have not invented a smart stop sign yet. Yeah. Imagine how much better we can be in just our traffic. That's an example of a simple intelligence on the edge. The FPGA is called Field Programmable Gate Array, and that is a kind of a chip that can be programmed in the field. Now, why do we need that in the edge? The problem right now here is that the artificial intelligence that will tell me, has the car really stopped, or the car has not stopped, or car was just crawling? Did it ever come to a stop? Did it stop behind the white line or not? That algorithm, the AI algorithm, is improving every day. So I don't have a fixed algorithm. So because the AI algorithm is fixing, now I need something so that I can add that intelligence and improve it as it gets better and better. Now, what do I mean by better? Like say somebody stopped, but didn't quite stop in the white line, but I'm willing to let that go. As opposed to a guy who didn't stop at all, or a guy who would have made a crawling stop. These are finer differences, and you can train your AI to do that, but that algorithm is going to be more sophisticated. So that is why you need an FPGA, because you can download your AI algorithm in that. But since the AI algorithm is changing, you need a flexible, field programmable machine, which is called FPGA. And so hopefully that explains what is an edge, what is an intelligent edge, and for the intelligent edge, why do you need an FPGA?
That's incredible. I actually wish that stoplight in Colorado and Denver, when I was driving through it last month, had a big sign that says we will take your picture and send you a ticket if you turn right on a red light, which I didn't know.
By the way, I mean, how easy it is to do that. I to be very honest, very easy. We have all the technology today to do that. And I think if we install in only 5% of the stoplights and the other 95% just simply says this might have that technology, right? And then if we start sending some tickets, that's it. And I know stop signs and right turns cause many accidents and cause safety issues. So I think that would be one very good example. Other thing is crime. I mean, I think if, generally speaking, if there are enough cameras and people knew that if they committed a crime, some camera will catch them, as long as that is true. And if those cameras are intelligent enough to keep those pictures, they somehow know this is not a normal picture. Something is happening that I need to keep this picture, but not that picture. How do you do that? How do you detect that this is some kind of a crime and this is not a crime? But I mean, we might not be there today, but we will get there, because as a human, when we see a picture, if I show you a video, you can quickly conclude that this looks like a little bit suspicious situation and I need to investigate more, right? As opposed to a normal parking lot that you're seeing, nothing is happening, and then you can say, this is a normal parking lot, there's nothing interesting to see here. So so intelligence at the edge, I believe, is very important. And I think right now, because of the AI, it cannot be done without a good FPGA running the AI algorithm.
Yes, I have my Ring doorbell, and of course I always get every time the neighbor's dog walks by, I always get a notification. But yeah, there's so many reasons why we need intelligent edge and why that needs to be a little bit smarter than what we're currently dealing with. I think that's great. Naveed, I've watched you. I've watched you speak many times, and I was hoping you could repeat to our audience how neuromorphic AI computing is important, and why is the technology so critical in the development of the Internet of Things?
Yeah, I think for normal people, I think without getting into technical things, I think it is important how our brain computes. And it is interesting. The brain actually is very good for computing certain kind of things, not every kind of thing, right? But in the situation, AI happens to be a scenario where actually brain might be a better machine. If you have to crunch through billions and billions of data, maybe our brain may not be a good machine to do that. But when our brain is well suited for that application, it does a remarkable job. It is a job which looks magical. It looks like, and the trick is that how the data is stored and how you act on it. So let me give you an example before I talk about neuromorphic computing. But let's imagine most of the time the reason our compute is designed is based on the idea we have a computing engine and we have a memory. So when you act on something, you go grab the memory on which you have to act on something. It may be an image, something. Then you do that action. You put the result back in the memory. Then you say, okay, what's the next step? Then you go grab that piece of memory or you act on that. But let's say all your actions are going to be on the same piece of memory. But our current computers cannot do that. The reason is because there is no way to store that image or that data in the CPU or where you're doing the compute. So even I could do that, I keep on moving it back and forth, back and forth, back and forth. That makes it very power hungry, it makes it very inefficient. But it's not true for other kind of application. For financial applications, that is not the case. For many other applications, that is the case. So that's why, generally speaking, computers are very efficient. But a new field, neuromorphic computing, tries to mimic a situation where you act like a brain. A nearest example we can give would be if you can somehow combine memory with compute at the same location. So the memory stays where it is. You can act on the entire memory, do something. Like, let's say it's an image. You want to change something about all the image, but you don't grab the image from anywhere. The image stays there. You do operate on it. Once that operation is done, you can say, okay, now I need to do another operation. So image stays where it is and you keep on operating on it. That means you have to combine compute and memory. So sometimes you call it at memory computing, sometimes we call it near memory computing. And I believe that is probably the easiest example we can provide to people without getting too detailed into how actually brain works. So I think that is the nearest example, that we need to merge the memory and CPU together. Now, why is memory and CPU not merged together to begin with? The reason is history. When we started the computing, the memories were invented, and the question was, how do you compute? And do you bring memory close? So the idea initially was that the focus was in CPU. There was a small amount of data. The data was always some numbers, an Excel sheet or something, whatever you want to call it. You bring in, you operate on it. So then people said, well, okay, I use this memory. So then we invented cache. So you have level 1 cache, level 2 cache, level 3 cache. So a caching system was invented because there was always a small amount of data on which the CPU is operating. Now invert the world. Huge amount of data, and CPU is doing small amount of work but working on each and every element of the data. That computing engine is built in a wrong way, right? Most real world problems are like that. When you're looking at an image, your brain is not doing a lot with every pixel. Your brain is doing little bit with a pixel, right? But it is doing on a big swath of that, right? So that's a very different, so that requires a different kind of compute infrastructure. Now, many companies like Amazon, Microsoft, Google, Meta, all of these people have figured out that their workloads that they're running also do not fit in a normal mode. So they are building their own accelerators, or they're building their own chips to suitable for that workload. So the future that you will see is that people will build workload specific chips. So we are moving from an era where we assume that there's a main CPU and there is memory, and no matter what workload you have, it's good enough, because our CPUs are very powerful and we had large enough memory, so it's good enough. Unfortunately, now data is huge, too big, and CPUs are not becoming fast and fast because of Moore's law is tapering off or it is dying. So now what do? If Moore's law is tapering off, you can't get any performance out of the CPU. Memory is not big enough. What do? How do you get more efficiency out of this whole thing? You have to think of new architecture. So neuromorphic computing is a kind of an architecture, a kind of a compute system in which you bring these things together.
That's incredible. Yeah, I'm so excited to see the future of where this is going to take us. And I keep talking and writing about the industry, and people say, "Oh, Moore's law is over," but yeah, we still have a long ways to go.
Yeah, I think in Moore's law, I think my understanding in Moore's law is that we are too stuck is what you can do at a chip level. I think we should think at a higher level. So the question is, okay, if I cannot double the performance in 18 months at the chip level, can I do that with chiplets putting in a package? Can I do that at the system level? Can I do that in a bigger level? As long as the client, the customer is getting the value, which is, in line with the inspiration of Moore's law, I think Moore's law lives. I think we should not be thinking of a single chip. Now, Gordon Moore, when he was talking about that, he was talking about that one chip, but that was 1960s. So fast forward where we are today, I think we should think about performance as it means to customer experience. So if the customer experience improves every 18 months through CPU, through software integrated into CPU, many chips integrating together, the whole system, I think we'll have to redefine our expectation from a system. And as long as that is happening, I think customers don't care. Customers don't care if the chip is doing 2x what it did 18 months ago. Customers care, am I getting a 2x experience in the 18 months or not? So I think we should think like that.
Right. It's so much of what goes into it is just magic to so many people. It's amazing. But Naveed, with the hundreds of billions of dollars being invested in the semiconductor industry around the world, where do you see the industry going in the future? What do you predict for the future of semiconductor industry?
So, first of all, it is my opinion when people ask me, do you think we have reached some kind of a crest in semiconductor industry? It is going to be downhill from here. Or so my opinion about that is we're just starting. The reason I say that, look at the last 40, 50 years of history. How many people have actually contributed to semiconductor industry? Very few. I would be surprised if that number is more than 500,000 people. And the number is even smaller who have made core contributions to the field. And I will always be surprised if it is the number of countries involved that is more than a dozen. It's actually fairly small from where this major. Now imagine for a moment the number of people contributing to semiconductor is 10 million, 100 million. Now imagine 100 countries around the world are fully involved and doing all kinds of material research, chemical research, electrical engineering, computer science, AI, name it, all that goes into it. Imagine that. Yeah. And that's what's happening now. People are waking up, they're understanding semiconductors are very crucial to my company, to my group, to my family, to my nation. This awareness is happening that they are not only crucial for your growth, they are crucial for your sovereignty as a nation, they're crucial for your defense, they're crucial for your medical system, education system, financial system, communication system, logistics, everything. When this realization is happening, nations around the world are now investing for these reasons. And now what net result will happen, millions of new people will come into the semiconductor industry. I'm very hopeful all those new people that are coming, all the new nations, all the new money that is coming is going to lead us to newer things. We took silicon, we ran with it, we took it all the way to the limit. I mean, today we are at 2 nanometer, going to 1 nanometer. I mean, if you had asked me 10 years ago, we will be here, I don't know what I would have said, but that looked impossible. But today, where we are, I think, but we push silicon. What about the other materials? What about other computing systems? Yeah. What about other different types of big material combined to create all alternate ways of achieving computing, memory, and other things? I think huge amount of innovation is possible. It is. I'll give you an example. We have been using batteries for at least maybe 100 years. I think the original battery was invented about 1,000 years ago, a very primitive one. But for the last 100, 200 years, we have been using batteries. And they were kind of the same. Mm-hmm. I think about 5 years ago, 3 years ago, we woke up. Humanity woke up. Silicon Valley woke up. No, batteries are really important. Oh, because of the autonomous cars, perhaps, because of some other reasons. Yeah. And now we have hundreds of battery companies. We have dozens of industries. I fundamentally think the entire battery industry is going to completely change in the next 5 to 10 years. And people have range anxiety in the cars, gone. People have safety concerns in the battery, gone. We'll have batteries for smallest IoT devices all the way to the cities will have batteries to give them, surge protection on their grid. Why? Because the humanity is now focused on battery. Similar way, I think humanity is now focusing on semiconductors.
Right.
That is going to lead to fundamental new innovations, new materials, new processes. More money will pick more attractive jobs. People will come in. I am terribly excited. I think next 50 years, next 20 years, next 10 years is going to bring a lot of innovation to semiconductor industry.
It's going to be so much. I mean, just what you and I were talking about before the show, how this younger generation is getting involved in the industry, and we need to bring this knowledge and experience and excitement about the industry to this younger generation, and explain to them what we work on, and explain to them how this equipment is. We're moving atoms. I mean, we're making transistors at atomic layers, and it's so important that we bring that attention to the younger generation as this industry continues to grow. And I mean, just photonics alone is a whole industry. We could sit down and talk for an hour about the future of photonics and where that's going. There's so much growth in the industry and where it's in the future.
Yeah, absolutely. I think unless we do a good job of exciting our next generation to come and join us, it would be impossible to make all the incredible things that we can make happen in semiconductor. I'll give you an example. The last few years, I've been quite involved with RISC-V. And if somebody had come and told me or you in 2016 that a day will come where 17-year-old folks will be designing microprocessors, and you will laugh at them saying, what are you talking about? Microprocessors, you probably go get a few masters and then a PhD, and then you go work for Intel or AMD for another 5-7 years. And then they will let you touch the microprocessor design after that. And that was pretty much true. Yeah. With the advent of RISC-V, we went to around 500 universities around the world, started those classes. And then I can give you 2 examples. In a third world country like Pakistan, in an undergraduate institution, which doesn't even have a graduate program, we have had a situation where 2 or 3 students under the guidance of a professor actually designed a RISC-V processor. We have an example of a 13-year-old who worked as an intern in our office at Sci-Fi and was able to make a RISC-V processor. Now, yes, RISC-V is very simple. RISC-V is, not as complicated as x86 or ARM architecture, but it is a fully functional microprocessor. And for many, many applications, it is perfectly fine. Now, if those 13-year-old and 17-year-old people can do that, that tells you that education campaign lead us there. If you have a much wider education campaign, what 13 and 17-year-old, they get excited about semiconductor, about our materials, about atomic level structures that we are creating, about things that are going to happen in quantum computing, things that are happening in things like graphene and a lot of other new materials that are coming. Even solar cells. I believe there's a lot more possibility as we combine various different layers in solar cells and improve them. That is a very important aspect of that, right? So I think it is absolutely crucial that our industry takes great interest in education, attracting the talent and younger generation, because we need a few million of them, because we have the work for them, we have the exciting projects, but we do not have the attention of the next generation as much as we should have. Secondly, I think we should also focus on other countries around the world, because I think there are, I can see 50, 25, 30, pick a number, countries around the world, good college system, great kids, can get them excited there as well. And then they can work, because of now work from home, work from anywhere, they can be in those countries and collaborate with us. And finally, I think a very big component is open source. Because I think if we can do a part of the project open source or whole project open source, it increases the collaboration. We saw that in RISC-V, we see that in other aspects. What we are doing now is that open source allows collaboration, increases innovation all over the world. And I think this is another reason why I think we should emphasize on education, open source combined together, and bring in new people in our fold.
Yes, yes. I have a vision of how open source is going to just explode the Internet of Things industry. I mean, they're talking about 1 trillion devices by 2030, 2035 or 2030. It's the open source will change the world as we know it with the Internet of Things and the way that we interface with our technology today.
I absolutely think so. I think if you ever work with, and I did work with the last 4 or 5 years with open source RISC-V, and I could see that when we went around, we did about close to 100 seminars around the world. Took me to all the many countries. I think there was a total of 65 or 70 countries around the world where we gave and do these seminars. You would not believe how people were thankful to us. They were so thankful that we brought this technology, educated them, and they could see a future for themselves. They could see that on their own, without asking anybody else, they can go to GitHub, download the code, and start building something, read the books, read the material, and be on a Slack channel, communicate with colleagues all over the world, and contribute to this. It's terribly exciting to see people excited. And they were so thankful that we were spreading the message. We need to do that on all other aspects of hardware. And I think once many nations and millions of people around the world start contributing and collaborating on these projects, I can only imagine what kind of new devices, new chips, new technologies, new processes will be invented, which we have not even thought about yet.
Oh, definitely. It's going to be an incredible future, I think. The semiconductor industry, the technology industry is going to be unrecognizable in 50 years from now. I think we're going to turn around and laugh at a lot of the stuff that we were working on today. But Naveed, I am sure so many of my viewers have a ton of interest knowing more about RapidSilicon. Can you tell me more about your company and how your viewers can learn more about your business?
Sure. So I think our motivation came from open source. And when we looked at RISC-V, we said, wow, a great revolution is going on. So, okay, after RISC-V, what you should do? So then we start looking at the edge. And the idea is that unless you connect the compute to the edge, you cannot take the next step. So now in edge, then you have to have intelligent edge. If you're going to have an intelligent edge, then you need an AI, then you need an AI, then you need an FPGA. So that's the journey. So the journey is, how can you make the edge intelligent? And that means you need to establish an FPGA company, which we did, which is specially designed to run AI algorithms more efficiently, but also it has open source software. The reason is because if you're thinking about democratizing FPGAs, which means millions of people all over the world are using your chip, you cannot possibly set up a support organization to answer their questions. If you cannot do that, the next best thing you can do is open source your software. They have a problem, they can download the software, figure out where the bug is themselves, or they can go on a Slack channel, somebody will answer that. Or there would be other support organizations that they can help them. But that way we could truly sell it to millions of people. Even somebody is buying 1 FPGA or 2 FPGA or 10 FPGAs, I don't have to worry about, well, this guy lives in the middle of Amazon jungle, how would I support him? Do I have to have a distributor in Brazil? What do I do? I don't have to worry about that. So I think the purpose and the goal of RapidSilicon is very simple. Let's democratize FPGAs. Let's make edge intelligent. Let's make sure that people are not waiting for us to answer their questions. Let's make sure that people can innovate on their own and contribute rather than just be a user of a technology. So these are the purposes. We have made a lot of good progress in the last year and a half. We're releasing our chip by the end of this year. Hopefully, we'll be able to demonstrate we have already released our software. Our software is already actually doing very well, which is surprising. Open source software is not expected to do that well against the commercial software, but our software is doing that. It's open source. You can go to GitHub, download it. You can work with us on any part of it, contribute in any way you want. So yeah, so those are the things about RapidSilicon that is important. Open source, democratization of FPGAs, enabling the intelligent edge, and that's kind of the key messages of RapidSilicon.
That's incredible. That's incredible. I think about how your efforts are just going to change the future of my children, my grandchildren. It's incredible how what you're working on today is going to change the future. And I'm so excited about being able to talk to you about that and having you on the show. If there is any need for any of our viewers for semiconductor equipment to either buy or sell, Move Technologies is always happy to help you. You can reach out to me on LinkedIn, or you can send me an email. The Move Marketplace is at www.moov.co. And again, thank you for watching the Movers and Shakers LinkedIn Live series. Have a great day. Thank you so much for being with me today, Naveed.
Thank you, Robert. It was my pleasure.
Great. Thank you so much. Bye.
Bye.